Alright, so in this tutorial we're going to introduce or reintroduce the idea of collisions and couple that with what we know about energy. We're going to do about 15 minutes worth of new material, and it's really not that new, it's just application to various problems. What we don't finish in this tutorial we'll pick up in class today. So the key ideas here, what we're going to focus on, are conservation of momentum and look at whether kinetic energy is conserved or not. Because momentum and kinetic energy are really two measures of motion. In fact, in the first blank, anything that is moving can be said to have both momentum and kinetic energy. They're based on the mass and the velocity. And both play a role in how the objects behave when they feel a force. And so with the collision, which is usually a sudden force, we want to compare and contrast the two and see how they combine to give us a complete picture of what's going on with the collision. So let's start by basically doing a comparison between the two and a quick little review, okay, between momentum and kinetic energy. So the equation for momentum, of course, is mv, and for kinetic energy it's 1/2 mv squared. So the notable difference there is that kinetic energy goes by the square of the velocity, whereas momentum goes linearly with it. Another important distinction is the type of measurement. Momentum is a vector, okay, whereas kinetic energy is a scalar. So momentum direction plays a very important role. You can have 5 objects each with their own momentum and get a total of 0, whereas with kinetic energy, if you have 5 objects with kinetic energy, there's no way they could ever add up to 0 because you can't have a negative. Why does one get a change in momentum? Okay, well, that's because you have an impulse. Oops, try that again. Okay, so we said that an impulse J leads to a change in momentum, and an impulse is really just the force acting over time. Whereas we change kinetic energy by doing work. And work, we said, is a force acting over distance. So they look very similar, but they give us different results. And probably most importantly, are they conserved during interactions? Well, with momentum, we said yes. For every type of situation, there is a conservation of momentum, unless there's an external force to our system. All right? With kinetic energy, is that always conserved? And the answer is sometimes. And we want to look at those situations where it is and where it isn't. Okay, so if you're wondering, well, wait, why sometimes, why not always? What's always conserved is total energy. Okay, so there's a difference. There's many types of energy. Kinetic energy is just one type of that. So if you take into account potential, total, or kinetic, and even thermal, then you can get conservation of energy. Okay, so that would be conserved. So let's do a quick little derivation right now that's actually pretty important. That is actually useful. And that's to express kinetic energy in terms of momentum without knowing how fast you're going. We know kinetic energy is 1/2 mv squared, but what would be the kinetic energy given a certain momentum? Well, that's a pretty simple thing to do. So we know that Ke is 1/2 mv squared, but we don't know v, so we want to substitute in momentum. We also know that velocity is equal to momentum divided by mass. Okay, so we just substitute in P over M for 1/2 mv squared. So we get 1/2 m P over M quantity squared. And if we simplify, we get P squared on the top. So this is Ke. And then we have the 2, and then we have M squared divided by M. So that would leave m divided by m squared, so that would leave an m on the bottom. And so we have a nice little equation that says kinetic energy is equal to the square of the velocity divided by 2m. And in fact, if we were to plot Ke versus momentum, we see that they're not linear with each other. There's a quadratic relationship. Okay, so doubling momentum, which can be done a number of ways, will give you 4 times the kinetic energy. Be careful with that. This is not in your AP reference tables. It's in the IB reference tables, but it's something I would write down. It's a useful relationship to know to go back and forth between kinetic energy. So a simple little problem we can do is, let's say we have a cat. It feels an impulse of 10 newton seconds when it's sitting there doing nothing, which means its initial velocity is 0. What is its kinetic energy? Normally we don't associate impulse with kinetic energy. but we do associate impulse with a change in momentum. So the change in momentum is going to be 10 kilogram meters per second, and therefore its final momentum is going to be 10 because initial momentum was 0. So now we can find the kinetic energy very simply by doing p squared all over 2m. We don't have to mess with finding the speed of the cat before, after, etc. So that's 10 squared all over 2 times 5, which gives us 10 joules of kinetic energy. So coincidentally here, the momentum and the kinetic energy take on the same value, but that's not always going to be the case. If the impulse was a double the original, what would be our kinetic energy? Well, twice the impulse will lead to twice the change in momentum, which will lead to twice the final momentum. And so KE is proportional to P squared, so that will lead to 4 times kinetic energy. Okay? So a small change in momentum gives us a large change in kinetic energy because, again, kinetic energy goes by the square of velocity or the square of the momentum. All right, so let's look at some other situations here. We're going to revisit collisions and conservation laws. So let's start with an inelastic collision, a classic, perfectly inelastic. Okay, so what does that mean? Basically, we have an object, let's say a bullet, fires into the block, and the bullet sticks into the block, and then they both move off afterwards with some velocity that way. So we want to look at conservation laws. So was momentum conserved in this case? Does the fact that the bullet embedded itself into the block change that? The answer is no. I mean, it doesn't change it, but momentum was definitely conserved because the force between the bullet and the block was internal to them, so there's going to be no external forces there. So what was the momentum and speed of the bullet block after the collision? All right, that's a problem we should be fairly comfortable with. We've done that before. Okay, so we got to say sigma p equals sigma p prime. So let's look at our before. Before, we have a mass of m, okay, moving with a velocity of v. We'll assume it wasn't given outright. It then hits after, and by the way, this block had an initial velocity of 0, so it was just sitting there. That's going to equal the total momentum after, which is going to be m plus 9m. That's the mass of the block. They go together as 1 times v prime. Okay, so in a classic inelastic collision, the masses combine and move off as 1. So if we solve for v prime, that's not too hard to see that it's 1/10 the original velocity. Okay, so that should be a problem we're very, very comfortable with, and we don't need to put in actual numbers to understand it. So the fact that the block has a huge mass compared to the bullet tells us it's going to move off with a relatively small speed. So the question is, was kinetic energy conserved there? Okay, well, we can look at KE before and KE after. So our original KE was 1/2 the little m times its velocity squared. Okay, that's pretty easy. What's our kinetic energy after the collision? Well, it's going to be 1/2, and we have a total of 10m after, and the velocity is 1/10 the original velocity. But we have to square that. Okay, so if we do the math, we get 1/2 10m times 1/100 v squared. And simplifying that, I'm going to leave the 1/2 out front for comparison. We've got 1/10 m v squared. So this is 1/20 mv squared, whereas this was 1/2 mv squared. So this has 10 times less kinetic energy. So was it conserved? No. Okay. And so an important lesson to learn here is that kinetic energy is never ever conserved in an inelastic collision, whether it be perfectly inelastic or partially. And you might ask, well, where did the lost kinetic energy go? We lost, let's see, 10 times or 90% of our kinetic energy. It went to thermal. Okay, so a lot of we went to Q plus KE prime. All right, keep that in mind. So let's go to another situation. Oh, I see. In general, any collision where KE is not conserved is considered inelastic. Okay, almost all collisions of this type, the greatest amount of kinetic energy is lost when the objects completely stick together. Okay, so we have what, 5 minutes left. Let's see if we can get through at least case 2 and maybe even one more and get this taken care of. All right, so let's look at a situation where we have an explosion away from one another. Okay, where we have an object, you know, think of the collision carts that are touching each other. There's a spring between them, and then after, one is going this way and the other is going this way. Okay, was kinetic energy conserved in this case? Well, we know momentum is conserved. That still holds. Okay, the total momentum, let's say, was 0 beforehand, so the momentum to the left has to be balanced by the momentum to the right. Well, is there a similar thing happened with kinetic energy? Well, let's see. What was our initial kinetic energy? 0. Neither were moving. What is our kinetic energy afterwards? Well, it's whatever. We have Ke prime plus Ke2 prime, right? There's two objects, but they're definitely not 0 because they can't cancel out because kinetic energy is not a vector, it's a scalar. So the answer is no, it was not conserved. So will kinetic energy ever be conserved in an explosion? The answer is no. And so even if the objects were initially moving and they pushed apart, there would still not be a conservation of kinetic energy. So if we started with 0 and we have some non-zero kinetic energy after, actually quite a bit, where did all that energy come from? Well, almost always is a release of potential energy. Okay, that could be chemical, if it's an actual chemical explosion. It could be elastic. In theory, it could be gravitational. Well, I'm not sure I can see gravitational coming on there. Okay, so we have two situations where momentum is conserved, but kinetic energy isn't, even though overall energy is. So let's look at one last situation. Now, I'll show this in class, but you may have seen before Newton's cradle, where an object of a mass comes in, hits a ball, and then the ball goes out with the same velocity. So if this is v, this comes with v naught equals v. We have one ball goes in, one ball comes out. If we were to drop 2, 2 would go out. If we were to drop 3, 3 would go out, and they would come out with the same velocity. Okay, so what's kind of remarkable about that, something that is not clear, is why does 1 come in, why does 1 go out? If 2 come in, why do 2 go out? Why couldn't we have 1 come in and 2 go out with half the speed? In other words, from a conservation of momentum standpoint, if we come in with a mass of m and a velocity v, why couldn't we have 2m go out with half the velocity, such that we get the same momentum? Why does 1 give 1, 2 give 2? Something else is going on here, because we could have many combinations of marbles going out for some coming in and still conserve momentum. Okay, so based on the law of conservation, we could have that. We could have 1 go in and 2 come out, or 3 come out. But what about kinetic energy? What would be true of that? So if 1 comes in and 2 go out, their speed would have to be the initial speed divided by 2 for reasons I just talked about, and the mass, of course, would be twice the mass. So let's look at kinetic energy here. So our kinetic energy to begin with is 1/2 mv0 squared, right? That's for this situation right there. And then let's say 2 come out. Well, our kinetic energy would be 1/2 2m times v over 2, or v0 over 2, quantity squared. So if I simplify that, 2 cancels out here, I've got 1/4 mv0 squared, right? Because of the 1/2 squared in here. And so I see I've got half the kinetic energy that I had before. Okay? So what makes this special? Why are we talking about kinetic energy? Because in this type of situation, this is called a perfectly elastic collision. Okay? And in a perfectly elastic collision, by definition, not only is momentum conserved, but kinetic energy is conserved. So let me say that again, because it's very important. If we're asking, is a collision perfectly elastic, I don't mean do they stick together or not. That's how I first introduced it.